Hi folks, today we're going to take a look at the algebraic process called factoring. Okay, now we're going to start by reminding ourselves what we mean by factoring when we're talking about numbers. So if I take the number 12, okay, and we ask you to factor that, you probably figure out we'll write it as a product of two smaller numbers. So I can write 12 as 3 times 4, or I could also write 12 as 6 times 2. Now, when we talk about factoring, we'd actually like to break it down into its simplest possible components. So not just write it as a product of two smaller numbers, but actually write it as a product of just prime numbers, which are the simplest possible numbers that we can work with. So here we can break this down further. 3 times, and then 4 can be written as 2 times 2. These are all prime numbers. Same thing here. 6 can be written as 3 times 2, and then times 2. So not only are we able to write the number in terms of a product of primes, we also realize that regardless of how we start breaking up the number, we always end up with the same prime factorization. That's actually a very important concept in math, which we talked about last time, the fundamental theorem of arithmetic, that any number can be written as a product of prime numbers in only one way. What we want to do now is see if we can extend this concept to algebraic expressions. That means expressions that contain both numbers and variables, in other words, polynomials. So let's take a look at an example that we're going to consider in a little bit. So let's say we have 3x to the 4, okay, minus 9x cubed plus 6x squared. So no like terms, so we can't simplify this any further. The question is can we possibly write this as the product of two simpler polynomials? That's our goal today. But I want you to look at this step. I want to write it as the product of two simpler polynomials. But we've already looked at multiplying polynomials. So we're actually going to use that to hopefully find some inspiration to go in the other direction. So I'm actually going to go and consider an example of using the distributive property. So I'm going to multiply the monomial 2x to the polynomial x squared plus 3x minus 4. Okay, notice here we have the product of two polynomials. So we recall the way we did this, we used the distributive property, and we had to multiply the 2x to every term in the bracket. Okay, so let's expand that. This gives us 2x cubed. Then we do the second one. That gives us plus 6x, and 6x squared, and then 2x times negative 4 minus 8x. Now, I want us to consider this polynomial that was in the bracket. Okay, notice there's nothing that's common to all three terms. This has two factors of x, because x squared is just x times x. This also has a factor of x, so they have something in common, but the third expression does not contain a factor of x. And when we look at the coefficients, the numbers 1, 3, and 4, there's nothing common to them, no factors that are common to all three. But when we look at the expanded polynomial, well, here I notice here I have a 2, a 6, and an 8. These three numbers all have a common factor of 2. They all contain a factor of 2. Okay, let's take it further and look at the variables. This has 3 factors of x, because x times x times x, x cubed. This has 2 factors of x, and this has just the 1. What do they have in common? Well, they all contain at least one factor of x. And we notice that these two numbers that are common factors to all three terms is exactly that monomial that we had in front. Okay, so we're going to try to use this as inspiration to go back to our previous example. Okay, 3x to the power 4 minus 9x cubed plus 6x squared. So let's see if we can find something common to each of these three terms. So let's start with the numbers. Here I've got a coefficient of 3, 9, and 6. Well, what factor do they all have in common? They all have a common factor of 3. Okay, let's take a look at the variables. This has 4 factors of x, 3 factors of x, 2 factors of x. So they all have at least 2 factors of x. This is what's common to all 3. Okay? So what I'm going to do is I'm going to see if what we had before will work here. I'm going to write this now as the common factor, which we determined was 3x squared, the factors that all 3 possessed. And then let's see what we have left once we remove these common factors. Well, here, if I remove the 3, well, 3 divided by 3 is just 1, so I'm just left with a 1 here. We know we don't write coefficients of 1, so I'll leave that. Here I had 4 x's, but I'm removing 2 of them. So what do I have? 2 left, x times x. Let's take a look at this here. 9. If I remove a factor of 3, well, what's 9 divided by 3? That's just 3. Notice here there's a subtraction. I don't change that. Okay. And here I had 3 factors of x, x times x times x, and I'm removing 2 of them. So I just have 1 left over. And plus, if we look at this term at the end, if I remove a factor of 3, well, 6 divided by 3 is 2. And here I had 2 factors of x, but I'm removing both of them. So there's no factors of x left. But look at what we've just accomplished. We've managed to take this polynomial up here and write it as the product of 2 simpler polynomials. Okay? Now, how do we determine what is simpler? Okay, well, the one thing is that the degree, the largest exponent, in this expression is 4. In these 2 expressions, they're smaller, 2 and 2, the largest degree, the largest power in each of these 2 polynomials. That's one way in which we consider one polynomial simpler than the other. The other way is if we look at these coefficients, they are all smaller than the coefficients in the original expression. Okay? So we accomplished what we set out to do, is we took a polynomial and we were able to write it as the product of 2 simpler polynomials. Well, we should actually check that here. So what we can do is redistribute and make sure that this is indeed equal to the original polynomial. So let's do that quickly. 3x squared times x squared. Yep, that's 3x to the 4th. 3x squared times negative 3x. 3 times negative 3, negative 9. X squared times x, x cubed. Yep, that's good. And then 3x squared times 2. Well, the only thing that's going to change is the number. So 3 times 2 is 6, x squared. So these are indeed equal. Okay. Now, the way we accomplished this was to look for a common factor to each of the terms. And that's why this particular type of factoring is called common factoring. Okay. Now we're actually going to learn other ways to factor polynomials. Okay, we'll talk about that next time. Let's do one last example just to hopefully check that we do understand this. So I'm going to start with the polynomial 12x squared y squared. Notice here, nothing says we have to be working with only one variable. Okay, and minus 18xy squared. Okay, so our first job here is to try to find the common factors. So let's take a look at the numbers first. Okay, well, 12 and 18, they both have a factor of 2. But remember, I want to write this in the simplest possible, so I'm just going to check to see if there's any larger factors that we can remove. Well, they also have factor of 3. Okay, but an even larger common factor that they have is 6. They both contain factors of 6. And when you think about it, that's really the largest one. So that's what we're going to remove. So in terms of the coefficients, the largest common factor, or greatest common factor, is 6. Let's take a look at the variables. So let's start with the x's here. We have an x squared, so 2 factors of x, and this has 1 factor of x. So what do they share in common? Well, they share one factor in common of x. Let's take a look now at the y's. This has a y squared, meaning 2 factors of y. This has a y squared. They share a common factor of y squared. So we can take that out. Now let's see what we're left with once we remove these factors. Well, if I remove the factor of 6 here, I'm left with, well, 12 divided by 6 is 2. Okay, here I've got 2 factors of x, and I'm removing one of them, so I still have one left. Here I have 2 factors of y, but I've removed both of them, so no y's left here. And minus, here, 18. Remove a factor of 6, what are we left with? 3. Okay, let's take a look. Well, we removed the only factor of x, so there's no x's left, and we removed the 2 factors of y, so there's no y's left. So that's it. That's what we're left with. And let's take a look. This is as simple as it gets. These two terms don't contain any more common factors, and we've managed to write it as the product of 2 polynomials. Okay, so again, this is called common factoring because you're looking for factors that are common to all terms in the original polynomial.